In this video, we consider the application of what you say motional EMF. Now here, I have a conductor of length L. It is fixed at one end and I am rotating the other end. I am rotating this end by keeping this end fixed. So as it goes, it will be completing a circle in the magnetic field. So as you rotate it, the magnetic field lines are cut by the conductor and therefore across the ends of the conductor OA, across OA there will be a definite amount of EMF induced. So how much is that EMF? This is what we want to find. So here I consider a very small portion of the conductor dx at a distance x from the fixed point. And let this be moving with a tangential velocity v. Then the EMF induced in that small dx will be given by dE will be equal to minus of V into dx we can say BLV4. Then this V, you can see this V is not constant because as you move from here the V value will be 0. As you move from here, the V will be increasing accordingly. That variation will be there. As that V is changing as per this one, as you move from the fixed point to the other end, we cannot take that V as constant here. So I rewrite that into another form, that minus V into x into omega into dx, where omega is the angular velocity of rotation, angular velocity of rotation of this, and that remains constant at every point along its length. And therefore, you can get an equation like this, that V equal to minus of V omega into x dx we get. Now this is the small EMF induced in this small length dx of the conductor. Now I can consider this kind of dx's throughout, and you can find the EMF in each of that dx and add it, you get the total. So for finding that, you will be taking this equation and integrating that one from where to where. Here x is the variable, x varies as dx from 0 to L. L is the length of the conductor. Therefore, the total EMF induced in that will be equal to integral dE, that's equal to integral V into omega into x dx from 0 to L, where this omega and V are constants, and therefore we can have the equation written as equal to minus V into omega into integral x dx from 0 to L. As you integrate this one, x dx become x square by 2, and applying the limits you will be getting induced EMF E will be equal to minus of V into omega into L square divided by 2. So across the ends of the conductor, between these 2 points, there will be an EMF induced, which is given by minus V omega L square by 2. So this is the case with a conductor which is rotating in the magnetic field. But but there are special cases coming. Suppose you take the conductor and rotate with respect to its midpoint. When you rotate that conductor with respect to its midpoint, for example, if I take that length and rotate with respect to this point, so you will be getting the EMF induced in that case will be 0, because when you take the midpoint and do the whole thing here, the integration limit will be from minus L by 2 to plus L by 2, and by doing that one you will be getting the whole thing 0. If you rotate it with its midpoint fixed, then you can understand. So this equation is very important for solving problems. Now I give you, this is according to what you say the BLV problem. Without considering this BLV problem, we can use another direct method to get this equation. Let us see that how directly we can get this one. Now, according to Faraday's laws of electromagnetic induction, we have the formula induced EMF is equal to minus d phi by dt. But as you rotate it with a definite angular velocity omega, this will be describing an imaginary circle of radius L. So within that circle, the magnetic field lines are being cut by this imaginary circle, and therefore the flux linked with that imaginary circle will be equal to B into A, that's equal to D into pi L square, I could write. Alright? Now if it is rotating with an angular velocity omega, that omega equal to 2 pi by 3, I can write. And therefore, you get induced EMF E is equal to minus of B into pi into L square divided by T, I could write. So when I substitute for that T, I will be getting minus of B into pi into L square divided by T is equal to 2 pi by omega. And therefore, induced EMF is equal to minus of B into omega into L square by 2. So you will be getting the same formula directly taking the case of what you say, taking the flux equation, that is Faraday's second law. Directly applying, you will be getting the same formula. Okay, so when you rotate a conductor in a magnetic field, across the ends of the conductor there will be an EMF induced given by this particular form. Okay.